Morning, guys. Excuse me. Today we're going to be doing our 6.2b integration by substitution day 2. We're just going to continue on here, and we are going to define our inner function u, and we're going to find what these integrals actually equal. And at the end, we're going to get to a couple tough ones, and I'm going to try to go quick. So, I've tried all year, but it hasn't worked so well. But I'm looking at here. When I'm looking at number 5, I can see the numerator and the denominator are exactly 1 power off, so I can kind of see the derivative of this bottom is going to be 4x to the third, and I really don't care when I'm saying 4x to the third. I really don't care about the 4. I'm more about the x to the third, seeing that x to the third is around there, because I can fix the 4 if I need to. So if you don't really need substitution, you don't really have to use substitution. If you're like, oh, okay, that's going to be a natural log, we're going to say, okay, this is going to equal the natural log of 7 plus x to the fourth plus c. If you notice, I don't need my absolute values on this one because there's no way 7 plus x to the fourth is ever going to go negative for whatever x I put in there. However, does this particular little bugger work? Well, I would say, well, what is the derivative of that? Well, the derivative of that is the derivative of the business divided by the business. And I'm looking at that like, well, it's really close, but I don't want that 4. Oh, okay, so I'm going to multiply by a 4th, and I've got it. Okay, so if you can just grab it without use substitution, that's fine. If you don't, look at the inner function. If you think it's a natural log, your goal is to try to integrate something like that, where you're probably going to have a constant out front. So I'm going to let u equal my 7 plus x to the fourth, which means my du is going to equal 4x cubed dx. And if you follow what I did yesterday, I solved my equation for dx, so I'm looking at du over 4x cubed. And what I do is I'm going to substitute in for my dx only and whatever I'm calling u, and I leave everything else. So this integral is going to, I'm not substituting in for my x cubed, I am substituting in for the bottom, and I'm replacing my dx with du over 4x to the third, and because that's multiplied, then I look and I kind of simplify my integrand, which is really the integral of 1/4 times 1 over u du, and remember that constant we want to pull out front. So then I get to the easy peasy part, because that's easy to integrate. Well, this integral actually equals my constant of a 4th times my antiderivative of 1 over u, which is ln u, absolute value of it, plus c. And again, back here at the beginning, they want my antiderivative in terms of x, so I got to go back and I need to back substitute and say it's ln of 7 plus x to the fourth plus c. And of course, okay, if you're being logical about this, you are taking the derivative of that every time to make sure you are correct, all right? Bottom line, I can kind of see the derivative of this denominator is nested in the top. Well, this next one, well, when I look at that, if you're thinking natural log, well, what is the derivative of 1 plus x to the fourth? Well, that's going to be 4x to the third. And is my x to the third part of the derivative, is that around in my function? And it's not, because that's an x to the first. Well, that's kind of throwing the natural log out of the mix for me. And so I need to look a little bit deeper, and when I look a little bit deeper, hopefully your eyes are gravitating to an inverse tangent, because what I really want to do is I want to get crafty, and I want to see that x is 1 plus x squared squared dx. Now, if I let my inside function right there, well, that's a 2x, okay. Now my derivative is present in there, okay? So that just shows me what my derivative is going to be. And if you don't need to see it, a lot of people don't need their use substitution with this, but I'm going to go with it. I'm going to say, okay, we're going to let u equal the inner function, which is an x squared. Well, that means du is going to equal 2x dx, which means my dx equals du divided by 2. Remember, I'm substituting in for dx, I'm substituting in for x squared. So that's going to make me rename my integral as x over 1 plus u squared, and my dx is going to be my du over 2x, and then I can look and see, oh yeah, those x's reduce out, and I have a constant of 1/2 times the integral of 1 over 1 plus u squared du. And it fits an inverse tangent. So this is going to be 1/2 inverse tangent of u plus c. And then I always have to remember to back substitute in for my u to say 1/2 equals, it doesn't equal, sorry. So I get 1/2 inverse tangent, u was x squared plus c. And again, like I said, you are always going to check these by taking the derivative of what we found. What do you mean? Well, if I took the derivative of this function right here, it's going to be 1/2 times, okay? Well, what is that? It's 1 over 1 plus u squared times the derivative of my u. Well, I can see that 2 cancels out, and this is going to give me x over 1 plus x to the 4th, which is what I started with, and that confirms that that is my antiderivative, all right? So why don't you go ahead and why don't you try to do this one and see if you can get it. And if you're thinking, whoa, I want to do one more with you, okay, well, look here. Look at my inside portion of the function. The derivative of that is 5. Notice it has no x. I can deal with any constant, so therefore I'm going to let u equal that. Okay, and if you don't need u substitution on this, that's fine. So what I'm going to do is I'm going to say, okay, u is going to equal my inner function, which is going to be 5x minus 7, which means du is going to equal 5 dx, which means my dx equals du over 5. Okay, so I'm going to substitute in for that and that. So that's getting me to redefine my integral as the cubed root of u, and my dx is going to be du over 5. Oh, that's the same as 1/5 integral u to the 1/3 du, because I want to see my power rule. So I integrate 1/5 times u to the 4/3. There's a 1 in front of that, so that's a 3/4 here, plus my c. That's going to give me what? 3 over 20, right? 3 over 20 u to the 4/3 power plus c. But we want our derivative, or we want our antiderivative in terms of x, because that's how it was given to us. So the last thing we do is we take 3 over 20 and we plug in to that 4/3 plus c, and we put in our 5x minus 7, and you check your answer, okay? Or if you want to look a little bit nicer and cleaner, you don't have to do this, but you could make this the cubed root of 5x minus 7 to the 4th plus c. You could call it either one. I typically would stop right there. But please, I'm not going to waste the time to do all these to check the derivatives in here. Hopefully you guys are doing that, all right? And if you don't, well, I hope you do. I'm just going to leave it at that. So number 8, I'm going to hit pause, and I'd like to see you come up with this. This is exactly like the problem before. Give it a shot. All right, now I said this one's exactly like before. And typically, we want to let u equal the innermost function. Typically, the innermost function. So what that's going to do, that makes me focus right here, and I know the derivative of 5x to the 5th minus 7, that's going to be some 5x to the 4th. Bottom line, I'm focusing on my x to the 4th being around there because I can deal with the 10 and the 5 in the end. So here's my u. So I go through and I let u equal x to to the 5th minus 7. I find my substitution, or I have my substitution for u. I have my substitution for du. I hence plug them in. And then when I plug them in, I can see that x to the 4th goes away. I can see that 5 and that 10 reduced to a 2. So I have a constant of 2 that I can pop out in front of my integral. And then I'm actually just integrating u to the 3rd du. That's the whole point of integration by substitution. It allows us to organize our work to nicely find the rogue number that's needed to find the correct antiderivative. What are you talking about, rogue number? We're really looking for this half that is going to go out in front of that guy. And then there we are, okay? So we're going to keep on a-trucking. And this one looks a little bit there, okay, the same. Well, I guess I kind of got to make some identifications here. And when I'm looking at this, I'm kind of looking at the bottom. A lot of times I'm looking at the bottom, unless it's in a square root or something. Even if it is, a lot of times I'm focusing on that. And I'm saying, okay, if I let u equal that, and this is mental math, I know my derivative of u is going to be e to the x dx, right? And I'm like, hey, does this part of my derivative, does it live in there? And it does. There it is, so I can deal with it. So then I continue and say dx equals du over e to the x, okay? So what I do is I rewrite my integrand, and I'm going to replace only what I said I was going to replace. This is the illegal portion, okay, of Kruger's method, which is a du over e to the x times by that. And because that's 2 times that on the top, well, I can actually reduce those out. Ooh, look there. I have a constant of 2. So that's actually making me integrate 2 times the integral of 1 over u du. Well, I know the antiderivative of that. It's going to be ln, absolute value of u, plus c. Don't forget your constant that's multiplied times it, because you actually have 2 of those, right? And then also, don't forget that you need to back substitute your u in there. Okay? Because we said u equal what? 6 plus e to the x. So we're really looking at 2 ln absolute value 6 plus e to the x plus c. There is my antiderivative. And like I said, let me beat this like a dead horse. Never stop there, guys, because this next test next week, you should know what you're going to get. Well, what is the derivative of this? It's 2 times, well, the derivative of the business here is just e to the x over the business, which actually equals 2 e to the x over 6 plus e to the x, and that's where I started from. Therefore, that's my antiderivative. You're always checking as you're moving along, okay? Then we get to number 10, okay? Do we have a derivative that is the tangent, meaning I know the derivative of sine is cosine, I know the derivative of cosine is negative sine, I know the derivative of tangent is secant squared, which isn't in here. I know the derivative of a secant is a secant tangent. I know the derivative of a cotangent is a negative cosecant squared. I know the derivative of a cosecant is a negative cosecant cotangent. But nowhere do I find the tangent as a derivative. Okay, well, here's where we got to get a little crafty. We got to think back to our pre-calc days. What? Yeah, I got to think back to my pre-calc days, and I got to think of, oh, what's another way to write the tangent x? Maybe sine 3x over cosine 3x. Okay, there we go, because that's equivalent to the top. Now, when I'm looking at things here, well, what do I got to do? Well, I'm saying we're typically using the innermost function, but of course, that's going to fail here. But let's look. Let's let u equal the cosine of 3x, okay? Because I want to find out if I let this be u, I need to see, can I find a sine 3x that's going to cancel that out somewhere? Well, this gives me du equals derivative of cosine is negative sine 3x times a chain rule, remember, times 3. So that is my derivative of that. And do I have it? Yes, I can absorb that sine 3x, and I can deal with that negative 3, because dx is going to end up equaling du over negative 3 sine 3x. Okay, so I'm going to go back and I'm going to make my substitution. I'm substituting out that for u. I'm substituting out dx for that. Okay, so I'm going to go make that substitution. So my u is down here. I have nothing for my sine 3x there, but my dx I am substituting in times du over negative 3 sine 3x. And as I reduce my integrand, I can see this sine 3x and this sine 3x goes away, which actually means I have a constant of negative 1/3 integral 1 over u du. Well, isn't that kind of nice? Because now this is super easy. It's negative 1/3 ln absolute value u plus c. But what is u? So it's negative 1/3 ln absolute value cosine 3x plus c. And that is my antiderivative, which means we just found a new antiderivative rule here, okay? We found a new antiderivative rule. What do you mean? Well, what we just found out here is we found out the integral of a tangent x dx is going to have to look like the integral from a sine x over cosine x dx, where the denominator is my u substitution. So the derivative or the antiderivative of a tangent x is actually going to equal, what is it going to equal? Negative ln absolute value cosine x plus c. Okay, so that's what it can be, and you have to be able to look at equivalence. And I'm going to find that because u equals my cosine x, which means my du equals, remember cosine is negative sine x dx. So when I do my substitution here, I actually get my negative is going to come out, right? And I have 1 over u du, which goes to here when I back substitute it for my u. Now you have to be able to look at equivalence. This actually equals the ln of a secant x plus c. And you might be like, because it might be a multiple choice problem, and that might not be your answer you're looking for. This might be the only one that's there, and you're saying, well, how the heck does that work? Well, remember, when I'm looking at a negative ln cosine x plus c, remember your properties of logs. This actually can come up and be a negative 1 up here. An exponent on that whole thing, meaning you're looking at the ln of cosine x. It's not the inverse, raised to the negative first power in this case, because that's a negative exponent that's coming up, which means a 1. This is an ln absolute value 1 over cosine x, which 1 over cosine x is a secant x, okay? Bottom line, there you go. Can look like that. What is Kruger trying to tell you here? I'm going to hit pause, and I'm going to write the 2 new ones you need to add to your, I don't want to call it a derivative list. These are going to be an antiderivative list. So I'm going to hit pause, and then I'm going to write them down. Okay, so if you don't want to have to go through all this substitution all of the time whenever you run into a tangent, if you just memorize the integral of a tangent x is negative ln absolute value cosine x plus c, it's great because it gets you to the end result faster and you don't have to do a u substitution. Also, the antiderivative of a cosine or excuse me, a cotangent x dx, well, that's a negative ln sine x. And the reason for that is simply because the way to rewrite a cotangent, well, that's a cosine x over a sine x, right, dx. So now u is going to equal sine x, which means du equals cosine x dx, which means my dx equals du over a cosine x, which means if I rewrote this integral, it's the integral of, there's my u, here's my cosine x, but my du is du over cosine x, and that cosine x cancels out, so it actually turns into the integral of 1 over u du, which is ln absolute value u plus c, which when I back substitute in my u, I get the top, okay? So those are two that if you don't want to have to go through what I just did right here, like every time you run into a cotangent, if you don't want to go through all that business all the time, that's fine. Then you memorize these two new rules right here, and you write them down on the sheet, and you take care of them. Okay? And we're going to move on. A couple tougher ones here. We got two more, and then we're going to be done. Notice, again, if I let u equal my whole inside function here, okay, and I took the derivative of that, du is going to equal negative 36x cubed. Okay, and what am I focusing on? I'm focusing on the x cubed. Does that x cubed, is this derivative living anywhere in here? And the answer is a big fat no. What does that mean? That means if I'm letting my whole u be there, that means this is not going to equal 1 over the square root of u in the end. I'm not going to be able to get by with that. Well, I got to get a little crafty. So you got to, not really crafty, but you got to look at your derivatives. Whoa, what's the only other one that has a square root in the denominator? Maybe an inverse sine or an inverse cosine. So if I was looking at this as the integral from 3x over the square root of 1 minus something squared dx, what is it in here that I square that gives me 9x to the fourth? Maybe a 3x squared, right? 3x squared times 3x squared. That gives me a 9x to the fourth. Ah, okay. And if I took the derivative of that 3x squared, that's going to give me a 6x. Bottom line, that's what I'm looking for. There he is. Ooh, I think I just found my substitution. Okay, so we're going to kind of come back, and I'm going to say, okay, well, I'm going to let u equal 3x squared. So du equals 6x dx. So my dx is going to be replaced with a du over 6x. Okay, I can do that. I'm replacing that, and I'm replacing that only. So this is going to give me my integral of my 3x stays in the top. I have a square root of 1 minus u squared, and then my dx gets replaced with a du over 6x, and remember that's multiplied. Because it's multiplied, that's the only reason. The only reason I can reduce out this x and this x, and that 3 goes to a 1, that's 6, will go to a 2. So I have a constant of 1/2 integral 1 over the square root of 1 minus u squared du. And when you look on your sheet, that is a template for an inverse sine, isn't it? And it's an inverse sine because it's not negative on the top. So this antiderivative is 1/2 times the inverse sine of u plus c. Remember, I got to put my u back in there because I need it in terms of x. So this is an inverse sine of 3x squared plus c. And let me beat it to death a little bit further. No, we don't stop there. We come back and we say, okay, what is the derivative of this? Well, it's 1/2 times the derivative of an inverse sine That's not sine to the negative 1. That's an inverse sine the way I wrote it, okay? And the derivative of that is what? It's 1 over the square root of 1 minus something squared times the derivative of my something. My something is 3x squared times the derivative of the something I put in there. That's times 6x, which is technically over 1. Well, that gives me 1 over, if I simplify, square root 1 minus, well, 3x squared times 3x squared, that's 9x to the 4th, okay? And this 2 reduces this to a 3, which gives me a 3x on the top. And is that where I started from? Why, yes it is. Therefore, that's how I know that is my antiderivative of it, okay? And the last one we get to here, we get to the cosine cubed x. Well, people are going to be looking at here and are really going to be kind of thinking about some stuff. And you're like, well, I can't really let u equal the cosine, because if u was the cosine, okay, if I let u equal cosine x, well then du is going to equal negative sine x dx, and there's no sine x in here that's going to get absorbed. Remember, this always gets absorbed and makes something, it reduces out with something in the original integral, and that doesn't work. And it's really a cosine cubed. Well, let's cut to the chase. Well, there are those things called trig identities. And cosine cubed could be rewritten as, with a big eraser, cosine cubed could be rewritten as a cosine x times a cosine squared x dx, right? I could do that. I could separate those, because remember, because I'm taking a derivative, and I know there's a chain rule in here somewhere, because I have something cubed, so I got to be able to take the derivative of my something somewhere, so I know the derivative of my trig function here, I'm going to need a negative sign or something in there. And so I split it apart, and then I remember, oh yeah, I remember sine squared x plus cosine squared x, that equals 1. So I know I could say a cosine squared x equals 1 minus a sine squared x, and I can introduce a sine in there. Okay, so this is going to give me a cosine x times 1 minus sine squared x dx. And I really have two paths that I can go on this. There's a couple ways to go. I could distribute my cosine, and I could say this is the integral of a cosine x minus a cosine x times a sine squared x dx. And then I could break this really using my properties of integrals, the integral of a cosine x dx minus the integral of a cosine x sine squared x dx, because I know the antiderivative of this first one. Okay, I know the antiderivative of a cosine, well, derivative of sine is cosine, so this is going to give me what? Sine x minus, but over here, now over here, if I let u equal that sine x, well then du is going to equal cosine x dx, so my dx is going to equal a du over a cosine x. So I can kind of say, hey, here is going to be my u squared. My cosine I'm going to leave there. That's going to be a u squared times dx is going to be a du over a cosine x. Oh, look at there. That's kind of, excuse me, nice. And I've already integrated the first part. And this is going to be minus the integral of u squared du in the end, right? Oh, this is the integral. It's not the integral, that's a sine, because I've already integrated my sine portion in the beginning. So this is going to give me a sine x minus what? U to the third, 1/3, plus a c. So this is a sine x minus 1/3 times what? A sine cubed x plus c. And if you got to go through and check this again, remember, okay, well, all right, let's check it out. Well, how does this derivative, if this is truly my antiderivative, when I take the derivative of all of this, I'm going to end up with a cosine cube. So derivative of sine is cosine minus, well, if I take this down, remember that's sine x cubed, so that 3 comes down and kills that, so it's really 1/3 times 3, which gives me a sine x squared times the chain rule, derivative of sine is times a cosine x. So these cancel out, so I get a cosine x minus a cosine x times a sine squared x. And you're like, oh, that's not a cosine cubed. Oh, but look at that. I have a common factor that I can factor out a cosine x using my trig identities, verify the identity. And that's going to, I just wrote that wrong. So if I took my cosine, my GCF of a cosine x out of there, well, that's going to give me 1 minus sine squared x. Well, what's 1 minus sine squared? That's a cosine x times, oh, that's a cosine squared x, and a cosine times a cosine squared is a cosine cube x. So yeah, it did work. There is my answer. Well, that was quite a bit, okay? Like I said, there's 2 paths to follow here, okay? And what's my other path to follow? Well, what is my other path to follow? Let's say I drew a line here, and I kept going down, and I got rid of all of this, okay? And let's say I came back here to the beginning, because this is path number 1. Path number 2 is going to be over here. If I say, well, I'm going to let u equal my, what, my sine x, I think I'm going to go with. Sine x. So the derivative of sine is going to be my cosine, isn't it? So du is going to equal cosine x dx. So dx is going to equal du over cosine x, okay? So I'm going to replace this, and I'm going to replace this inside here, okay? And this is a product. This is why I can. This is this times dx. So my integral is actually going to be cosine x times 1 minus u squared, where my dx is going to be a du over a cosine x. Check it out. This is all over 1, so the cosines are going to cancel, okay? And then that's going to give me the integral of 1 minus u squared du. Well, I can integrate this. This is the antiderivative of 1 is going to be u, because I'm in terms of u, minus a u squared came from a u cubed with a 1/3, because I need a 1 there, plus a c. If I back distribute what u was sine x. And what I do is I get to sine x minus 1/3 sine cubed x plus c. Bada bing, bada boom. There's 2 different ways to substitute that, but in the end, I still, because I don't have anything for the cosine cube, I need to use a trig identity to break this into an integrable function, if I can terminologize it that way. But they get a little bit harder and craftier. Well, how do I know when I have to do that? Well, when we let u equal cosine up here in the beginning, if we said, oh, u is going to equal cosine x, and if you did that, you are committing this to be the integral of u cubed du, right? So then du equals derivative of cosine is negative sine dx, and then if I substitute it in there, I get dx equals my du over negative sine x, okay? And here's where you're going to see it, because you're going to be taking that substitution, let me get rid of some of this stuff here, and you're going to run into a dead end, because you're going to be getting the integral of, remember, here it is, that's my u to the third, my dx gets replaced with du over negative sine x, and there's no way for me to get rid of that. That's not a constant. I can't pull a function out in front. I can only take constants out. So there's no way for that to go away. That's how I knew that's the wrong substitution. So then I broke it apart. I redefined it as an equivalent using trigonometric identities, all right? And that rounds us out for substitution. Tomorrow we will be evaluating definite integrals using substitution. Kind of fun. There's two ways to do that. And you should be good to go, hopefully, to do any and all of your homework in 6.2b. Hope you had a nice day. Hope this makes sense. If it didn't make sense, I really hope you reach out to me and ask for some questions that we can maybe Google Meet or something and straighten them out for you. Have a good day. Bye-bye.